Hello everyone and welcome back to another video. Today we're continuing the Kalda Mechanics series, and we're still in the statics section, and today we're going to try to do maybe 2 problems because one of them is really quite tricky and I expect it's going to take a while to explain. Okay, so let's start off with number 5. A block rests on an inclined surface with slope angle alpha. The surface moves with the horizontal acceleration a, which lies in the same vertical plane as a normal vector to the surface. Determine the value of the coefficient of friction mu that allows the block to stay still. So this isn't actually a very complicated problem. This is kind of a standard problem you see in a lot of mechanics textbooks, and let's go through it. And oh yeah, also, although it's moving with an acceleration alpha, this is actually still a statics problem, and ignore this because it's the snippet took a part of the rest of the handout. But anyways, so even though it has an acceleration, this is going to be a statics problem because we can transform into the accelerated reference frame. And in the accelerated reference frame, since this is not slipping, it must have no acceleration, and so that's statics, right? So let me redraw the diagram here, and I don't know, I'm drawing the box, but so you have the inclined plane like this, angle alpha, and here's the block, and this is going to be the reference frame that's going at a. It's accelerating with acceleration a, and that means there's going to be a fictitious force on the center of mass with magnitude ma and is horizontal. And let's also draw the other forces. There's mg, and there's going to be the normal force and the friction force, which could point this way or that way depending on the magnitude of the acceleration, but that's not really what matters right now. So we could try to use some fancy tricks or whatever, but I think it's simplest to just do force balance on the direction perpendicular to the plane and the direction parallel to the plane. So let's start off with the direction perpendicular to the plane. If we let this be n, then we have n minus a, and this is alpha here, so the component perpendicular is going to be ma sine alpha, and this is just regular minus mg cosine alpha is equal to 0. So this gives us that the normal force is equal to ma sine alpha plus mg cosine alpha. So we just need to find the friction force now, and we can do that by balancing forces on the direction parallel to the plane. And that basically gives us that this angle is alpha again, so ma cosine alpha, so minus ma cosine alpha plus mg, so that's going to be sine alpha in this direction, so plus mg sine alpha, and we'll just let friction force be positive in this direction, but that doesn't really matter because we're going to have to take the absolute value anyway since mu is positive. And so the friction force, which we'll denote S of F, is equal to 0, and this implies that F sub F is equal to ma cosine alpha minus mg sine alpha. And so we want the range of coefficients of friction, so we kind of want to find the maximum coefficient and the minimum coefficient of friction that is required, and the minimum coefficient of friction is when S sub F is equal to mu n, and if F sub F is equal to mu n, then we can divide these two equations, and that gives us mu is equal to, all the m's cancel, and it's a cosine alpha minus g sine alpha over a sine alpha plus g cosine alpha. So this is the minimum value of mu, so mu has to be greater than or equal to this value here, so we can replace that with a greater than or equal to sign. And one thing we have to watch out for is that this top value can actually be negative, especially if acceleration is in this direction, or in this accelerated reference frame, which means that the plane is moving backward. So like you're pulling the plane out from under the block and it has to stay with the plane. So we're just going to add some absolute value signs here so that gets taken care of, though that doesn't really matter because if it's negative, you're just going to flip the sign, right? And we also probably want to add a condition that this is only possible when this is greater than 0, because otherwise, if this is less than 0, that means that the plane is being pulled out too fast and there's no normal force, and then it obviously can't be in contact. So we also require that this denominator, a sine alpha plus g cosine alpha, is greater than 0. And this is kind of evident because if you get to 0, this value becomes undefined. So that was a bit of a simple problem, and let's move on to the next one, problem 6, and this one is very tricky. A cylinder with radius r spins around its axis with an angular speed omega. On its inner surface there lies a small block. The coefficient of friction between the block and the inner surface of the cylinder is mu. Find the values of omega for which the block does not slip. Stay still with respect to the cylinder. Consider the cases A, where A, the axis of the cylinder, is horizontal, B, the axis is inclined by angle alpha with respect to the horizon. So this problem has a lot of stuff going on, and basically it's just like the previous problem. There's motion, and the way we deal with that is we take the rotating reference frame. And with this one, with part A, it's quite simple to see. Where you need to place your like cross sections, because we're gonna work in 2D since 3D is difficult, and what accelerated reference frame we want. But in B, it gets a little bit more difficult. But we're just gonna start with part A and see what happens. So in part A, it's completely horizontal, and we're looking at it from this perspective here, if you guys can see what I mean. And this the cylinder is rotating like this at omega, and let's focus in on this block in the accelerated reference frame. So if we focus in on the block in this accelerated reference frame, there's going to be a fictitious force here of m omega squared r, right? The centrifugal force, because we're in the accelerated reference frame. And oh, it's a bit thick, so let me just reduce it. And there's also going to be gravitational force, and there's going to be the normal and friction force. And we're going to use the trick used several times in the first video of this series, which is that the normal and friction force, when we're looking at the boundaries like minimum or maximum, is going to point with this angle being arctan mu, since the coefficient of friction is going to be fully, I guess, saturated. So we're going to use that, but we also need to take care of the gravitational force here. So if we look at this, here the gravitational force points like this, but when it's rotated to, I guess, here or here, the gravitational force points like this, and here it points like this. So if you guys can kind of see what's going on, is this in this frame, well, in this frame gravitational force is just pointing in one direction, right? But in this frame it's going to be rotating, since this ground is always going to be parallel to the floor. So the gravitational force is going to be the one rotating, and we can kind of see that it's rotating like this. So it might be better if you imagine yourself actually on here, and you can see that the gravitational force is going to move from like your right side to your left side, and like up and down. So gravitational force is going to point like this, rotating around the circle where this is the center of mass. And basically one trick we can do here is we can describe the set of the sum of these two, the sum of the gravitational force and the centrifugal force, as a circle. And we can just do that by directly placing this circle onto here. So let me erase this label and make the vector a little bit larger so we can actually see what's going on. So this is the centrifugal force. It's always going to be pointing down because it's always pointing outward. And then the set of the vector sum of the gravitational force and the centrifugal force is like this, because the gravitational force is rotating. And then at each of these points, somehow the friction and normal force have to be this vector here, so that they point and make the net force 0. But let me erase that line there. And basically, this is going to be bounded by the fact that there's a maximum angle at which this friction force, friction plus normal force, F sub F plus N, can point, because it's going to be bounded by arctan mu on both sides. So the maximum angle at which it points, which is going to be at tangency, has to be less than this value, because otherwise it won't be able to reach the point when it's so if it was farther away, and let's say this was arctan mu, and right now it's still able to reach the circle when the circle is farthest away, I guess, creates the largest angle. Then let's consider it when omega is I guess smaller, and it's going to be like this. Then when the gravitational force plus centrifugal force ends up here, then the normal and friction force aren't able to cancel it out. So that's how omega is going to be bounded. And so to find the maximum omega, to find the minimum omega, then we have to look for this tangency condition, because the entire circle has to be contained within this arctan mu, these boundaries of the arctan mu, so that the net force is still able to be 0. But if it's farther away, then obviously it's going to happen, so we're going to find when it's tangent. And this happens when omega squared r is going to be mg times this, mg divided by sine of this angle here, which is arctan mu. So m omega squared r is equal to mg over sine alpha, over sine, not alpha, arc tan mu. And this is for minimum omega. And this gives that, well, these two cancel, and this gives that omega squared r is equal to g over, and if we imagine the triangle here, it's mu and 1, so it's root mu squared plus 1, so sine is mu over root 1 plus mu squared. And so we can actually divide this here to make it a little bit nicer, and this is going to be g times root 1 plus mu squared over mu, and pulling it in, the mu squared is going to cancel, and it's going to be 1 plus 1 over mu squared. And this is for minimum omega, so we can replace this with a greater than or equal to sign, and omega squared r has to be greater than or equal to that value for when alpha is equal to 0. So now you have to work with when alpha is not equal to 0. So this is going to be really tricky, but basically what we have to consider is the frame that contains the plane that contains the gravitational force, the one that's going to be rotating around, and the centrifugal force. And the way we can do that is we're still taking the rotating reference frame, but in the rotating reference frame we can just choose the plane correctly so that it contains a shape like this. In this one it was very easy, we could have just looked at it from this perspective, but This one is going to be a bit more difficult because of this tilted axis. But one thing we can do is say that both of them will lie, the two of them will define a plane, and we're just going to use the plane that contains them, and then from there we can work from there. So now looking at the plane, we have to consider the set of points again, in which the centrifugal force is still going to just point downward from the block, m omega squared r, but the gravitational force is going to be a little bit different. It's actually not going to be the full circle. And so the way you can look at that is you have to actually look at it from the outside perspective and see how the gravitational force is going to be pointing. So we're just going to consider the extremes here, and so I have to keep scrolling up and down. I guess I'll just draw the picture here again. And there's a block here. And this angle is alpha. And we can consider the extremes of when the block is at the bottom and when the block is at the top. So when the block is at the bottom, gravitational force is pointing like this, and centrifugal force is pointing like that. And I think it's pretty clear here that the angle between the two vectors is going to be alpha. So in the plane containing the two of them, we have this m omega squared r, and the gravitational force is pointing leftward like this, mg, and that angle is alpha. So let's consider the top. It's going to be something like that here too. Gravitational force is like this, and centrifugal force is like this. And with a little bit of angle tracing, it's not really that difficult. It's 180 minus alpha. And since these are the two extremes, everything is going to be bounded by them. And you can kind of see that by working a little. And I think the best way to see in which way it actually rotates is to, instead of considering the block here, is to consider yourself or a person. So at the bottom, the person is facing like this, and so the person is facing like this, and so this is like he's standing here and he's looking this way. And if he's looking that way, the gravitational force is pointing to his right. And now let's move to the top. At the top here, he's going to be standing like this, and since he's rotated, he's not going to be facing this way. Since he was facing this way before, he's actually going to be facing that way, and we'll just see his hair here. And from there, we can deduce that the gravitational force is pointing to his right again. It's pointing to his right and making an angle 180 minus alpha. So basically, it starts from pointing here to pointing here as it rotates from the bottom to the top. And this is the range of value. This is the set of locations in which the mg vector can point. So instead of having this full circle of points here, we actually just have this range, this arc here, with this angle being alpha and this angle also being alpha. I hope that made sense. And from here, it's actually nearly the same calculation as before, except that we have to watch out when alpha is too big and there's actually no tangency condition. I'll try to explain that in a bit. So if we assume that alpha is large enough, then we can just make sure that the circle is contained within the bounds with arctan mu. Oh, that was really messy. But we just have to make sure the circle is contained within these bounds of arctan mu. And that's going to be the same calculation as before, and that's going to be omega squared r omega squared r is greater than or equal to g times root 1 plus 1 over mu squared. But the only issue is if this sector here isn't that big. And if alpha is pretty large, then the sector might just point like this. But the tangency is here, so we can actually be closer in. The circle can be closer in because the gravitational force like that, because these lines, the gravitational force plus centrifugal force never actually reach these areas. So let's try to find when the alpha is small enough such that the tangency occurs. And that would be if alpha is less than this value here, when alpha at this value here is 90 minus arctan mu. And 90 minus arctan mu, and we can move it over, and this gives us mu is less than tangent 90 minus alpha. So if this is the case, then omega squared r is greater than or equal to this value. However, if it isn't the case, then we can just move it in. And if we move it in here, we can just use law of sines to find the value of omega squared r that is required. So law of sines gives here that, well, so this over this, the sine of this value is going to be constant. So mg over sine of arctan mu, mg over sine over arctan mu is equal to omega squared r, m omega squared r, divided by the sine of 90 minus alpha minus arctan mu. And after some calculations, this is going to give, and I'm not going to do this because this is just math. This is going to give us that omega squared r is greater than or equal to g times cosine alpha minus cosine alpha over mu. And this is if mu is greater than tangent of 90 minus alpha. And that's the end of that trig problem, and that's going to be the end of that video because this video has gone really long. And I hope you enjoyed it, and thanks for watching.